Good evening, everyone. I am Dr. Mujib Chaudhary, postdoctoral fellow at UT Dallas. It's my pleasure to welcome you tonight's webinar in computational science. Thank you so much for joining us tonight. Today we have Dr. Asim K, postdoctoral fellow at UT Dallas, as our keynote speaker. He is a visiting scholar at Princeton University. He will be joining as a tenure-track assistant professor at the University of Texas, El Paso, in this fall 2021. Dr. Asim K graduated from Dhaka University with his bachelor and master's in applied statistics. Here is the format of today's event. The event duration is 1 hour, 40 minutes, first 40 minutes keynote speaker's talk, followed by 10 minutes question and answer. Finally, Dr. Jalal Ahmed, principal investigator of ICM, will make the concluding remark and comment. So if you have any questions related to talk or higher studies here in United States, please feel free to comment below or ask after the speaker's talk. We can take you in our studio. Now let's get started. Dr. Asim K.
Thank you so much, Mujib, for the introduction. And I'd like to thank all the organizer for inviting me to share my research with all of you. Let me first share my slide. Can you see my
Yes.
slide?
Yeah, we can see your slide.
Okay, thank you so much.
You're welcome.
So today I'm going to be talking about a new clustering algorithm for multi-layer complex network based on topological data analysis. And here is the outline of my presentation. First, I will briefly talk about complex network and its extension to multi-layer network. Then I will briefly introduce the concept of topological data analysis. After that, I will describe our proposed clustering algorithm for multi-layer networks. I will also briefly talk about some theoretical properties of this clustering algorithm. So to assess the performance of this clustering algorithm, we apply the proposed algorithm to some simulated complex network. So I'll show these results. So in a case study, we apply this clustering algorithm to a climate insurance multi-layer network. I'll show the performance on this case study also. And finally, I'll conclude and we'll show some future directions. So we can represent different complex systems with a network. For example, we can study the relationship among different banks with a network, or we can study the connectivity among different airports with a network. So all this network can be represented by a graph G, for example, where V is the set of nodes and E is the set of edges. Here, omega is the edge weights. And here, N is the total number of nodes in the network. So I'll show you a few examples in a minute. So, and the connection between different nodes in the network can be represented by N by N adjacency matrix A. So the idea here is if two nodes are connected by an edge, the corresponding elements of this matrix will be the corresponding edge weights. And if two nodes are not connected by an edge, the corresponding elements will be 0. And for simplicity here, we assume that the network is undirected. That is, the edges are undirected. For example, here we have two complex network. In the left-hand side, we have French power grid, where the nodes, the points, represent power station, substation, or generator. And the connection between two nodes, the lines, represent transmission line. So these lines are not the distribution line, which actually comes to our home or our school. These are high voltage transmission line. from power station to power station or power station to substation and so on. So in the right-hand side, we have US airline network on May 5th, 2020. So here the blue points, the nodes represent airports. And if two airports have direct flights between them, they are connected by an edge. So as you see here, so this is a reduced version of US airline network on May 5th because of COVID-19, because of the social distancing and mobility restrictions. And as you see here, the fresh power grid has 677 nodes and 913 edges. And in the right hand side, we have the US power grid, and the US power grid has 319 nodes and 4980 edges on May 5th, 2020. So now consider two different complex network, right? So suppose US airline network and US power grid network. Or for simplicity, let's consider Bangladesh airline network. So we have a airport at Chittagong, we have airport at Dhaka, Sylhet, Rajshahi, and so on. So we can consider this airline system with a network. And in the top, let's consider Bangladesh power grid network. So this power grid and airline network are highly interdependent. So think about if something happened to the power grid or power station near Chittagong Airport, it obviously affects the Chittagong Airport, right? So the functionality of Chittagong Airport will be damaged or affected by the damage of the power grid. So that is we can study the interdependency of these types of complex network with a multi-layer network. So we have YAM single layer network, G1, G2 up to GM, and with their adjacency matrix, A1, A2 up to AM, right? So here we have two different types of matrix. We have within layer matrix, which represent the dependency among different nodes in one single network. And also we have the relationship between two different networks, like GK and GL. So to define the relationship between two networks, we define a cross-layer adjacency matrix, S sub KL. Okay? So that is, in a multi-layer network, we have two types of adjacency matrix. We have within layer adjacency matrix A, and we have like between layer adjacency matrix. So this is the set of between layer adjacency matrix. So now the idea is, how can we define the cross layer edges? Okay, so the idea here is, if a cross layer edge UV is like that, so here one node belongs to like one network. Think about Bangladesh airport network, and the other node V belongs to like Bangladesh power grid network. So they are connected by these edges UV. And in general, we can model these types of relationship with a Supra adjacency matrix. Here, the diagonal elements are the within layer matrix, and off diagonal elements are the cross layer matrix. So that is the they represent cross layer connections. So this is a toy example of a multi-layer network. So here we have 5 layers, and each layer has like 7 nodes. So as you see here, we have two types of edges. We have solid line and we have a dashed lines. So solid line represent within layer connections, and the cross layer represent connection between two different layers, two different networks. So now the issue is here, all these interdependent complex systems are highly vulnerable to different types of hazard. So it could be natural hazard, it could be cyber attack. So that is, if something happened to like power grid, it affect the entire airline network or some other network. So now the question is, which segment of this multi-layer network are most vulnerable in terms of particular hazard? And can we isolate this unhealthy component, like vulnerable component? And that's how we can mitigate the risk of further failure propagation. So think about something happened to power station near to Chittagong Airport. So it might affect the Chittagong Airport, but can we somehow isolate this area so that if something happened to that area, it might not affect the other area, like Dhaka Airport or Sylhet Airport? So this is the objectives here. So we want to partition or cluster a multi-layer network into different communities. So I just want to tell you, you can stop me anytime if you have any question. So if you want to ask in Bangla, you can also ask in Bangla. So just stop me anytime if you have any question. So now the challenges here is we have multi-layer network. So we have two different types of relationship. We have within layer relationship, like suppose relationship within power grid network, and relationship within airline network. And also we have cross-layer relationship. So we want to capture both these types of relationship. And, and these different types of layers exhibit different types of local and global structural properties. So another important feature for multi-layer network is higher order network structure, like network motif or higher order topological feature like Betty numbers gives us stronger signal of community existence compared to lower order connections like edges. So we want to incorporate all these issues. And in order to incorporate all these issues, we introduce the concept of topological data analysis. So topological data analysis is a very emerging field of research which work at the interface of algebraic topology, statistics, machine learning, and data science. So the TDA, which we call topological data analysis in a short form, so it actually improve our understanding on the hidden rules of geometry and topology of a complex data set. And so many of you are mathematicians, you know much better than me about topology and topological features. So there are few key advantages using these types of approach in clustering. So one is topology studies the shape in a coordinate-free manner. It's very important. And it studies the properties of shapes, which are robust to minor perturbation. And it actually deals with compressed representation of shapes. So suppose we have two data sets from two different sources. So we can study their topological feature combinedly based on these approaches. So the ultimate goal here is to bring the tools from algebraic topology to study different complex data sets. So this is the outline of topological data analysis. Suppose we have a point cloud in the matrix space. So the idea here is from this point cloud, we actually construct nested simplicial complexes. So I'll talk in a minute briefly. And from this nested simplicial complexes, we extract topological features. And then we apply these extracted topological features in studying, for example, clustering, change point detection, price prediction, and different applications. So suppose we have a point cloud X in the matrix space, and then an abstract simplicial complex over X is a collection C of finite subset of X, such that the condition is that if sigma belongs to C, then a subset of sigma also belongs to C. And if the order of sigma is p plus 1, we call sigma is a p simplex. So this is an example, like few example of simplexes. So a point is a 0 simplex, an edge is a 1 simplex, and so on. Okay, so then a simplicial complex is formed by doing all these or many of these simplex together. The idea is here, the condition is the intersection of any two simplex is also a simplex. For example, think about these two simplex, one simplex and two simplex. So the intersection of these two is nothing but this, and this is also a simplex. So there are a number of simplicial complex in the literature, for example, check complex, Vittorus-Rives complex. So in our study, we are focusing on Vittorus-Rives complex. So this is a brief idea how this Vittorus-Rives complex work. So suppose we have a matrix space. We have a point cloud in the matrix space. Okay, so the idea here is if the distance between 2 points in the matrix space is less than some threshold nu, they are connected by an edge. So initially we have nu equals to 0. So that means all these points are disconnected. Then we increase our threshold nu equals to 0.15. As you see that a number of points are connected by an edge. In the next steps, we again increase our threshold. We get a more dense graph. Again, we increase our threshold. As you see, we get more denser graph. That is, by increasing this threshold, we get a nested sequence of graph. And this technique is called network filtration. And for each steps of this filtration, we extract topological features like Betti numbers, persistent diagram, and so on. So now the question here is, which of these extracted topological features are topological signal and which of them are topological noise? Okay, so the idea here is if some topological feature survive longer in the filtration process, they are topological signal. And if some feature like die quickly after their birth, we call they are topological noise. And we have three main summaries of these topological features. So one is called Betti numbers. So informally, I am telling you that the Betti number is nothing but the pit Betti number is nothing but p-dimensional hole in the simplicial complex. For example, beta 0 is the point like disconnected point cloud in the graph, and beta 1 is the number of one-dimensional hole in the graph. Beta 2 is the number of two-dimensional hole in the graph, and so on. And then another feature is called barcode plot. So we can study how long a particular topological feature survives in the filtration process based on barcode. So a longer barcode means they survive longer. A smaller barcode means they die quickly after their birth. And another feature is called persistent diagram. So this is also where the x-axis represent the birth time and y-axis represent the death time of a particular features in the filtration process. So this is an example of barcode in the left hand side and persistent diagram in the right hand side from 100 point clouds. And here in the top, you see the red bars represent how long a one-dimensional hole, that is beta 1, survive in the filtration process. It is a longer bar represent so this beta 1, this one-dimensional hole survive longer compared to the other small. And these black bars represent disconnected components in the graph. And in the right-hand side, we have persistent diagram. Again, the x-axis represent the birth time and the y-axis represent the death time of these features in the filtration process. So now the question is, which of them are topological signal and which of them are just topological noise? So the idea here is, if a topological feature lies near the diagonal line, they are topological noise because they die quickly after their birth. And if this lies far away from the diagonal line, they are topological signal. So again, the black points are for beta 0 and this red triangle for beta 1 for one-dimensional hole. So in our study, we use persistent diagram as a summary of these topological features. Okay, so suppose we have 2-point cloud in the matrix space. So we can compare the shape similarity of this 2-point cloud by comparing their persistent diagram, from the computed from the filtration process. Okay, so for example, here we have 2 persistent diagram and we superimpose one to another. So you see the distance. So this is a toy example of the distance between 2 persistent diagram. But there are many sophisticated metrics in the literature to compute distance between 2 persistent diagram. So one is called Weierstrass distance. So we can compare the shape similarity of 2-point cloud in the matrix space based on this arc Weierstrass distance. This is the summary. This is the whole summary of this topological data analysis approach. So we have a point cloud in the matrix space. So as you see, our beta 0 is 100. So they are, because they are disconnected, right? And with threshold 0, then we increase our threshold. Here we set epsilon or nu equals to 0.1. So as you see, many points are connected by an edge. And again, if you see clearly, it looks very small. Let me try to make it bigger. So as you see here, beta 0 is 20. So we have two. Yes. Try to be. Do you have any question? Okay, let me. So here we have 20 disconnected components. So that's why beta 0 is 20. And we have, as you see, beta 1 is 3. That means we have 3 one-dimensional hole. So you can see here 1, 2, and 3. That's why we have beta 1 is 3, and we don't have any 2-dimensional hole. That's why beta 2 is 0. And then the next steps, we increase our threshold. We get more dense graph. We have only like beta 0 is 3 because we have 3 connected components. And on beta 1 is 5. We have 5 one-dimensional hole, and so on. And from this filtration, we compute barcode and persistent diagram. So this is the steps of Tda approach. So now another important feature of is node embedding. Think about, we have a multi-layer complex network. So the idea here is we want to like transform this multi-layer complex network to a lower dimensional space. To do this, we actually use some kind of node embedding, so which extract or transform this multi-layer network to a lower dimensional space. And the important part is we want to preserve the structural information of this multi-layer network. Remember, we have 2 different types of relationship. We have within layer relationship, we have cross-layer relationship. So we want to capture this relationship while we want to transform this multi-layer network into lower dimensional space. So this is a very famous algorithm to transform multi-layer network to lower dimensional space, which is called main multi-layer network embedding. So we, in our study, we apply this main algorithm for transforming multi-layer network to lower dimensional space. Okay. So after transforming this multi-layer network to lower dimensional space, then we apply our Tda approach. So the idea here is if 2 points are close enough to group into one cluster or one community, if their local neighborhood has same similar shape. Okay, so suppose we have this point cloud xn in the matrix space. Okay, so for each xi in this matrix space, we actually select a neighborhood ni. So then in this neighborhood, we apply network filtration, this Tda approach we described earlier. And from this network filtration, we construct persistent diagram. That is, then we repeat this procedure for each of these points in the point cloud. So for each point in the point cloud, we select a neighborhood, we apply network filtration, Tda filtration, we construct persistent diagram. That is, for each point, we have a persistent diagram. And then we compute the pairwise distance between this persistent diagram. That is, we have a persistent distance matrix finally, which represent the pairwise persistent distance between 2 points in the matrix space. And then for a particular threshold k, so we select a threshold, and if the distance between 2 points is less than k, they're connected by an edge. Okay, then finally we count how many connected components in the graph, and these are our clusters. Okay. So this is the summary of this clustering algorithm. So initially we have these multi-layer networks. Then we apply this node embedding main to like transform this multi-layer network into lower dimensional space. And for each point, for example, for this point, we select a neighborhood Ni. We apply Tda approach, Tda filtration, and construct persistent diagram on this neighborhood. And we repeat this procedure for each of these points. Then we get this y-certain distance matrix. So when we get this distance matrix, we apply linkage clustering. So this is the graphical representation, what actually we are trying to say here. So suppose we have these points, so we have 3 different colors here. And we want to cluster these points like red, blue, and green in terms of their neighboring shape similarity. As you see, the red points, the neighborhood of red points are like heart-like shape. So we want to cluster them in one community or one cluster because their neighborhood are heart-like. So this is a very toy example. So this is not like mathematically correct, but just for visualization what's going on there. And for example, the green points has moon-like shape, moon-like neighborhood. So we want to cluster them in one group, and so on. All right, so let's see. So now we also study the theoretical properties of this clustering algorithm. So we're working on this area. So it's easy to like prove different properties for k-mean clustering, for example. But here our space is different. It's not this is not Euclidean space. So we're trying to prove, for example, the stability properties. So the stability property is that if you randomly select 2 samples from your original sample, and if you apply a clustering algorithm, then the distance between these two clustering results will not much like will be less than some threshold. This is the idea. So it's easy to prove for k-means, but for our case, as I told you, that is the space is different. We're working on that for last 1 year, but we don't have the results yet, final results yet. Anyway, so let's see. So now we actually compare this proposed clustering algorithm to other standard clustering algorithm like K-mean, K-midways, and hierarchical clustering. So, but notice that all these standard clustering algorithm like K-mean, K-midways, hierarchical clustering, they are all based on some kind of Euclidean distance. So they're all. So that's why they actually ignore the shape similarity or geometry of the data set. So, but our approach actually mainly focusing on geometry of the complex data set. And so in our study, we also tried to improve the K-midways standard K-midways by replacing this Euclidean distance with the Weierstrass distance matrix. So the all other steps are same, but we actually replace the Euclidean distance with the Weierstrass distance. And these are the standard validation measures to compare different types of clustering algorithm, like within sum of square, between and sum of square, and WB ratio. So a smaller WB ratio is better. So now we apply this clustering to two types of simulated network. So we want to compare how this proposed algorithm perform compared to other standard algorithm in some simulated networks. So initially we simulated one two-layer multi-layer network. So suppose think about Bangladesh airline network, and in the top Bangladesh power grid network. We have two-layer multi-layer network. So here each layer have 500 nodes, and in the first network has 700 edges, and the second network has 750 edges, and so on. So here both networks are generated from Adjacency random graph. So the Adjacency random graph is based on binomial distribution. So the edges are randomly assigned. So and we actually assign 200 cross layer edges. So we have two layers, and then we have cross layer edges. We assign 200 cross layer edges, and these are the Supra adjacency matrix of this two-layer multi-layer network. And we also need these edge weights both in within layer network and cross layer network. So we assume that the weights are from different uniform distribution. Okay, so then the second experiment, we have three-layer multi-layer network. So think about we have Bangladesh airline network, Bangladesh power grid network, and in the top we have Bangladesh telecommunication network. So we have three-layer multi-layer network. So and then again we assume that the first layer has 400 nodes, 600 edges. Second layer has 400 nodes, 500 edges, and so on. And here we actually draw graph G1 and G2 from Adjacency graph, and graph G2 are from preferential attachment graph. So we want to generate the graph from different structures, because think about the Bangladesh airline network and Bangladesh power grid network. The properties obviously different in this network. So we want to check how this algorithm perform for when we select each layer from different graphs. So G2 is from preferential attachment graph. So the idea here is, so it's like a richer will be more richer, the idea. So the connection of a like higher degree node will get more connections. So richer will be more richer, these types of things. But Adjacency graph is like we assign the edges completely randomly. And again, the edge weights are assigned. The first edge weights are from uniform distribution, and edge weights for G2 graph 2 are from normal distribution. Edge weights for graph 3 are from normal distribution, and so on. And again, we assign different number of cross layer edges. So the number of cross layer between graph G1 and G2 is 150, graph G2 and G3 are 200, and so on. And again, we assign the edge weights of this cross layer cross-layer edges from different normal distribution. And this is our Supra adjacency matrix. So we have two multi-layer networks. We apply our clustering algorithm, and we also apply different standard clustering algorithm. So these are the results, final results of this simulated experiment. So again, I am telling you that smaller WB ratio is better, and CPD is our proposed clustering algorithm, clustering based on persistent diagram. And this is the standard hierarchical clustering. And this is the k-medius clustering with the standard Euclidean distance. And this is the k-medius for using OSS distance. So as you see, WB ratio is smaller for CPD compared to the any other. And between the sum of squares should be larger. So obviously, so the variability so between two different layers will be higher if your clustering algorithm performs better. So if you see here, so CPD gives us much better performance compared to the other standard algorithm. And same thing for the experiment too. Now think about this k-medius with OSS distance. If you compare k-medius this with OSS distance with k-medius with Euclidean distance or standard hierarchical distance, you see that k-medius with OSS distance gives you much better performance compared to the other Euclidean distance-based algorithm. So now we actually apply this algorithm to a real-life network. So it's a real-world climate insurance multi-layer network. So the idea here is so this is actually for climate insurance risk, and this is a statistical summary how extreme weather event increased in last few decades. So it's like extreme precipitation, relative occurrence of extreme precipitation compared to some standard period. So as you see, the last few decades, the relative number of extreme precipitation increased like around 40%. And simultaneously, so it's in like in North America or in Western countries, so everything like have insurance. So you have a house, you have insurance, like but anything you have insurance. So if anything happened to your house, you claim that okay, my house got damaged from hails or storms, so give me the money. So this is the issue here. So if these types of extreme event increase significantly, insurance industry will lose billions of dollars. So they want to see which area of a particular country are more vulnerable in terms of these types of extreme events. So this is the idea here. So we have some data for Ontario, Canada. So we have in some insurance data, for example, number of insurance claims, total number of home insurance losses in a particular period, and average age of the house, average credit score of the owner, and total precipitation, like total rainfall or total snowfall, right? So on that area. So we want to cluster the area based on these types of variables. So what we did here, so this is the special distribution of these features. So this is a total. So this is the Ontario, Canada. So if someone live in Canada, they know much better than me. So this is the Ontario, Canada. And so this is the distribution of total number of home insurance claim, okay, and total amount of claim, and this is the total precipitation. So as you see here, this area has much more precipitation because it's near the lake. And this is the average credit score and average age of the house. So we want to cluster this Ontario, Canada based on these 5 variables. Okay. So what we did here, we create a multi-layer network, the 5-layer multi-layer network. And so each layer corresponds to either insurance variable or climate variable or socio-demographic variable. Okay, so the idea here is we want to capture the relationship among different variables. So you see the variables are from different source. Some are from insurance company, some are from precipitation related variables, and some explain their socio-demographic or economic status. So we want to capture the variability or dependency of all these variables. So this is a very complicated stuff. There are some non-linear relationship exist among these variables. Okay, so what we did here, again, we create a multi-layer network. And here we actually create a fully connected network. So we said, okay, all these nodes. So here the nodes are the FSA. It's like a postal code. Okay, the like postal code. Then we have like around 520 postal code in Ontario, Canada. So these are our nodes. And then we connect the nodes based on the correlation. And so as you see here, we have 504 FSA finally, like 504 postal code. And for each postal code, we have 5 variables. And then we create a multi-layer, 5-layer multi-layer network. And we actually define a 7-layer cross-layer edges. 7-layer. So we actually assign that, okay, layer N is related to layer L. That means number of insurance claim related to amount of loss. So amount of precipitation related to amount of loss and so on. So we have 5-layer multi-layer network and we have 7 cross-layer dependency. Let me, I should go fast. Okay, but the issue here is I told that, so the data source are different. They're messy, multi-resolution, and there might have non-linear relationship among them. So we can do a simple stuffs. We can use something called multivariate similarity matrix. But this is very linear stuffs. But there might have a non-linear relationship among these variables. So to capture this non-linearity, we use this multi-layer network approach. So again, after creating this multi-layer network, we apply this CPD algorithm, our proposed algorithm, and also some other standard algorithm. So again, you see that WB ratio of CPD, our proposed algorithm, gives us a much better performance compared to any other standard algorithm. And if you see this k-medias with this Poisson distance also gives us much better performance compared to the Euclidean and hierarchical distance. And this is the output like clusters based on this 4 clustering algorithm. As you see, this A are based on k-midways, and B is for our proposed algorithm. And this is the hierarchical clustering. As you see, it makes a very big clusters. And then D based on k-medias with Euclidean distance. And we also study the cluster features. So, okay, we got these clusters, and then we study, okay, let's see what is the summary features of this each cluster. So this is the class. So we have 15 cluster based on CPD algorithm, and we study the summary like what is the average credit score, what is the average claim or average houses of each clusters. So as you see that CPD also gives 2 big cluster, and we study their properties. We found that the house age of cluster 1 is much higher compared to the other. So this is actually urban area. So the houses in urban area is much higher compared to the rural area. And if you see the hierarchical clustering, the feature, as you see, it makes a very big cluster. The 87% nodes in the network belongs to one cluster. So because it ignores the geometry or non-linear relationship among different variables in the network. So in summary, here we actually propose this clustering algorithm based on topological data analysis. In particular, we use persistent diagram to capture the geometry of the complex data set. And we found that this proposed approach gives us much better performance compared to the others. And in a case study, we present or we develop a joint analysis of climate insurance network. And I can tell you that this climate insurance network is like very new stuff. So climate network studied before, but climate insurance network jointly eh, is very rare. So to study the interdependency among different complex variables, so using these types of approach will give us much better performance or much better representation of the complex data structure. So I think I have 2 minutes. Just let me give you some future plans. So this topological data analysis is a very new and emerging field of research. So we can not only use them to clustering a multi-layer network or clustering a complex data set, we can also use change point detection. So nowadays there's a huge interest in blockchain network, cryptocurrency blockchain network, for example. So we can study a blockchain network on different times. And if you want to see if there is any change point in a particular period, so we can use these types of topological features. So we study for each time what is the certain topological feature looks like. So then we can compare this topological feature over time. So again, we can do the we can also study the change point detection. This is a pilot study from our research. So we compare the proposed Tda based change point detection with other standard algorithm. So we found that this Tda based algorithm gives us a much better performance compared to the standard algorithm. And also we can study different multivariate time series through topological data analysis. So we have similar features. We can also study, and suppose we have a multivariate time series. Okay, so here we have 3 time series, for example. So we want to study, for example, how this multivariate time series evolve over time. So we can use this TDA type approaches here. And also because this is a very new area of research, there are lots of works to be done. In particular, there are theoretical statistical properties. Okay, so for example, their consistency, their asymptotic properties, hypothesis testing, confidence sets. So there are lots of things to be done. This is a very new emerging field, and they have huge application nowadays, not only in complex network, but also in any types of data set, like which we can represent or we can convert to a matrix space. This is some references. Um, the work is mainly based on this paper. Oh, thank you so much for your attention. And please ask me question that I'm telling you. Ask me question.
Thank you, Dr. Oshim. Is there any question?
Okay, I have many questions actually.
Oh, great.
Before that, let's go to the question regarding the comment section.
Yeah.
So, Oshim, can you see the question on the screen?
Give me 1 second. Let me stop sharing then. Stop sharing. Yes. Yeah. I see. Yeah. So okay. That's right. Somebody told. Okay. Yeah. Dr. Mujib told. This is not topology. That's true. This is not exactly topology. So yeah, this is. So the idea here is to bring the tools from algebraic topology to study the complex data set, like between numbers, persistent diagram, these type of things. So this is very new. So the idea here is, so far in statisticians, they do not focus on the geometry of the data. So this area is really completely ignored. But now people are trying to see, okay, what about the geometry of a data set? So now the question is, how can you study the geometry of a complex data set? Now, then either you have to do some types of computational geometry tools, like I forget. There's some similar tools like between numbers or persistent diagram, Bernoulli diagrams type things. So yeah. So now this is how we can quantify the geometry of a data set. Yeah, this is not exactly topology. That's I agree. But yeah, there are many questions. Some pure mathematician may thought, okay, this is not this what they are doing. This is not exactly. Yeah, there are some issues there. That's why I'm telling you that there are many things to be done there. Yeah.
Yeah. Thank you, Asim. There is a misunderstanding. Actually, you are reading from the comment section. Someone commented about the what is it is whether point set topology or applied topology. So
Oh, okay.
actually, I
I
was
see. No,
asking.
but
Yeah.
I understand. But still, this
Yeah.
is not exactly pure topology. Or so
Yeah.
I'm also very very scared to say, okay, this.
Yeah.
But because the there is no solid foundation still developed for this area. Yeah.
Yeah.
So I don't know. You guys know about Dr. Carlson from Stanford. He actually developed this area. He's a famous topologist, applied topologist from Stanford. So he first introduced this concept to applied researchers.
Okay. Okay, Oshim, there is another question on the screen, not on the comment section. On the screen, what kind of software you use for coding to optimize the noise?
Yeah, that's a good point. There are multiple software now available for this topological data analysis. So because I'm using this R-based software, and there are also some called parcels. So there is small software written in C. So people are using all these types of topological data analysis or extracting topological feature. So parcels, and there is some other topologic other software. Maybe yeah, I can email the link. Then maybe Mujib maybe forward or somehow set this.
Okay, we'll put in the comment section later after finishing
Yeah.
the live.
Yeah.
Okay, next, Ferdos, you have a question.
Yeah, I have a few questions. So I'll ask one by one, এবং আমি বাংলাতে জিজ্ঞেস করব কারণ আমার মনে হয় যে এখানে ভিউয়াররা অনেকে মানে বাংলা কোশ্চেন করতে একটু হেজিটেট বোধ করে, এজন্য অনেকে করে না, এজন্য আসলে এনকারেজ করার জন্যই শুরু করতেছে। তো যেটা হচ্ছে আপনি যেই অ্যালগরিদমটাতে প্রথমে যে ইটারেশন স্টেপটা যে ইউজ করেছেন, কতগুলো ইটারেশন, আপনার কোনো মানে স্টপিং ক্রাইটেরিয়া ছিল কিনা? আপনি কোন পর্যায়ে গিয়ে বলবেন যে ওকে আমার ক্লাস্টার গুড এনাফ ফর মি?
That's good. It's like experimental.
Okay.
Yeah.
Trial and
This
error.
is an experimental. So we actually, for this project, we go increase 0.1. So 0.1, like 0 to 1, we normalize the data 0 to 1. So the distance are from 0 to 1. Then we actually goes 0.111, like 0, 0.1, 0.2, 0.3 up to 1.
আচ্ছা, আরেকটা হচ্ছে আমি আপনার ওই মানে লোয়ার ডাইমেনশন এমবেডিংটাতে খুব একটা ফ্যামিলিয়ার না, এই জন্য কোশ্চেনটা করা। যেহেতু মাল্টি লেয়ার নেটওয়ার্ক মানে হচ্ছে প্রত্যেকটা লেয়ারে ডিফারেন্ট ক্যাটাগরিক্যাল রিলেশনশিপ, ডিফারেন্ট ক্যাটাগরি অফ রিলেশনশিপ। এখন যখন আপনি ওয়ান ডাইমেনশনে নিয়ে আসতেছেন, তখন এই সবগুলা এমনও কিছু দেখা যাবে যে টু নোটস এর মধ্যে মাল্টিপল টাইপ অফ রিলেশন আছে। এইটাকে কিভাবে ওয়ান ক্যাটাগরিতে নিয়ে আসতেছেন? সব
there's the like this is the main issue here. So we are obviously we are losing many information here. So yeah, but so this is the concern here, that okay, we are transforming this multi-layer network to lot. So though this paper is like a huge thing, they did all this. This is mainly based on matrix factorization, the algorithm. So, but obviously we are missing some information here. That's no doubt.
Yeah,
But
because
so far this is the
sorry for
this
interrupt.
is the best approach now.
বেশ না, মানে আমার মেইন যখন আমি মাল্টিলিনিয়ার নিয়ে কাজ করি, তখন আমার মেইন প্রবলেমটা থাকে যে আমি একটা ক্যাটাগরির সাথে আরেকটা ক্যাটাগরি কম্পারেবল কেমন করবো। কারণ যখন দুইটা ক্যাটাগরিকে এক করব, তখন দুইটা ক্যাটাগরি সামহাউ আমরা একটা মানে ডিস্টেন্স ম্যাট্রিক্স করে ইকুইলাইজ করতেছি, বা সাম কাইন্ড অফ ওয়ান ম্যাট্রিকে নিয়ে আসতেছি। এটা প্রবলেম যখন ক্যাটাগরি নিয়ে কাজ করতেছি। আমি বলতেছি যে স্নোফল কাম হাউস রেট, ওকে, they cannot be together, how come? So অনেকগুলো ইনফরমেশন এখানে লুজ করতেছি।
Right. So this is like, I can tell you, this is like a principal component analysis.
Yeah, that's true.
Right. This is like a principal component. So we don't know exactly finally what's going on there, but we actually extract this principal component.
আপনি এমবেডেড করার পরে যেটা ওয়ান ডাইমেনশন, সোফার ওয়ান ডাইমেনশনে নিয়ে আসছেন নেটওয়ার্ক, এরপরে আপনি আপনার অ্যালগরিদমটা ইউজ করেছেন, যেটা এখন আপনি যখন বেঞ্চমার্কিং করেছেন, দেয়ার আর ডিফারেন্ট অ্যালগরিদম, নেটওয়ার্ক ক্লাস্টারিং অ্যালগরিদম, নট k-means যদিও এরা হচ্ছে ইউক্লিডিয়ান ডিস্টেন্স বা ভেক্টরাইজড ডেটা ইউজ করে, কিন্তু দেয়ার আর আদার কাইন্ড অফ অ্যালগরিদম লাইক নিউটন গিরভান, তারপরে মডুলারিটি অ্যালগরিদম, যারা নেটওয়ার্ক স্ট্রাকচার নিয়ে কাজ করে। আপনি আপনার অ্যালগরিদমটাকে কি নেটওয়ার্ক স্ট্রাকচার অ্যালগরিদমের সাথে বেঞ্চমার্কিং করেছেন কিনা?
So far আমরা করি নাই।
আচ্ছা।
So we tried some other standard algorithm, but yeah, we don't do these types of what you say, this type of we don't compare.
কারণ আপনার ইনিশিয়াল ডেটা, আপনার মেইন ইনিশিয়াল ডেটাটা হচ্ছে নেটওয়ার্ক স্ট্রাকচার বেসড ডেটা। আপনার মূল ক্লাস্টারের আইডিয়াটাই হচ্ছে নেটওয়ার্ক স্ট্রাকচার। রাইট। এরপরে আপনি শিফট করে গিয়েছেন ইউক্লিডিয়ান ডেটাতে। রাইট। মানে আমার কাছে মনে হচ্ছিল যে এটা একটা কি টেরিটরিটাকে দেখা ঠিক কিনা, যে আমি
that's a good point. So our main concern was after embedding. So we thought, okay, let's do the embedding first, then let's see what happened. So yeah, but what you are telling, okay, yeah, we can also consider without embedding somehow initially. Maybe we have multi-layer network, we have this adjacency matrix. From there, we can do the clustering or not. Yeah, if we can do this, this will be great. Yeah, that's a good point.
আমি এই জায়গায় আপনাকে একটা রেফারেন্স দিতে পারি, যেহেতু আসলে দ্য নেটওয়ার্ক টপোলজিটা আসলে ডিফারেন্ট সেক্টরে এটা স্টাডি হচ্ছে। সোফার আমি যখন একটা রিভিউ পেপার লিখতেছি, তখন দেখতেছি আসলে ডিফারেন্ট সায়েন্টিফিক কমিউনিটির মধ্যে কোনো ইয়া নেই, মানে ইন্টারসেকশন নাই। এই সেম মাল্টিলেয়ার নেটওয়ার্ক নিয়ে মেশিন লার্নিং এ একটা পেপার আসছিল 2013-এ, এটাকে ওরা বলতেছে ক্রোমাটিক ক্লাস্টারিং। আপনি এটা একটু দেখতে পারেন। ওখানে যদিও তারা হচ্ছে মানে এজ এমবেডিংটা ইউজ করেনি, বাট ইট ক্যান বি এ ডিফারেন্ট গুড এরিয়া টু লুক এট। আমার আরেকটা কোশ্চেন হচ্ছে যে আপনি যখন এম্পিরিক্যাল ডেটা নিয়ে কাজ করলেন, মানে পারফরমেন্স দেখতেছেন, পারফরমেন্স দেখাতে হাইস্ট কত বড় নেটওয়ার্ক নিয়ে কাজ করেছেন আপনি?
So here, so in the simulation, we did like 500 nodes, 700 edges approximately in each layer, and you see in the case study we have 504 nodes. So we have 504 FSA in Ontario, Canada. It's not too big. That's what I'm telling you. It's like medium size. And this timing is an issue because I'm running all this code in my laptop. So, and yeah, this the computational cost is huge when you apply this TDA filtration. Maybe we need to do some server if we have very big network, like 2000
Okay,
nodes.
so what's the complexity of your algorithm?
So this is the thing. So now actually we are not, so in this paper, we're not focusing on this complexity right now. So we thought, okay, let's do let's study the algorithm first. Let's see the performance. Maybe next level we study the complexity. Maybe for what we do, can we do the parallel computation or not? So right now we are not like we're not focusing on the computational cost. Yeah, but this is for big network. We need to think about that. Yeah.
লাস্ট আর একটা কোশ্চেন করি আমি আপনাকে, সেটা হচ্ছে আপনার ক্লাস্টারিং কোয়ালিটি মেট্রিক গুলি যেগুলো দিয়েছেন আপনি, এই সবগুলি হচ্ছে ডিস্টেন্স বেস মেট্রিক।
That's right. That's true.
কিন্তু আপনার ইনিশিয়াল নেটওয়ার্ক কিন্তু ক্যাটাগরি।
Yeah. So I'm going to again. So because we actually mainly focusing on after the embedding stuff. So that's the issue here. So because we are thinking, okay, let's do the embedding and then see what's going on there. So that's why. So we tried some other. So they gives us similar results, but yeah, because this is a distance metric, because we convert all these things to a one-dimensional space or two-dimensional space.
Yeah, my concern is your cluster quality, everything you are doing, the performance, the quality metrics, everything is coming from your embedded metric, embedded network.
That's really.
But your original data is categorical data. Yeah,
categorical.
I know. Multilayer network, different kind of
different category, like
different is আছে আপনার correlation clustering.
We are running out of time.
Sorry.
আমি অনেক কোশ্চেন,
maybe we can discuss you later.
Yeah, sure. Yeah, definitely.
Thank you.
আমি আসলে এই এরিয়াতে কাজ করি, তো এইজন্য আপনাকে অনেকগুলো কোশ্চেন করার ছিল।
Thank you so much, because I have similar question like you also when I started working on it. So similar question. Yeah.
In future we can listen a talk from Ferdos about the data science, since he has more experience in applied data science working in the industry. We hope so. So now I'd like to recruit Dr. Jalal Ahmed, principal investigator of our ICM, to make the concluding remark for today's event. Dr. Jalal Ahmed.
First of all, thank you, Dr. Asim, to deliver his nice presentation, especially though he is from statistics, but he is applying the whole concept of pure mathematics. That means the topological analysis we taught in the mathematics department. We have a couple of courses on topology. Now he is using this concept in statistical data. That is a very important idea for the student on mathematics and statistics both. So again, I appreciate Dr. Asim for his nice presentation. So I think we can end up here. Thank you very much.
Thank you, Dr. Jalal Ahmed. Some audience, they're asking about the paper Asim already presented. So we'll give the link where the Asim's paper published in the comment section. I think we can end here.
So I can give you the preprint because it's not published yet. It's accepted in Proceedings of National Academy of Sciences. Maybe it's coming within a month. But I have the preprint, so I can send Mujib the preprint.
Yeah.
So anyway, so Dr. Asim, did you publish your thesis in the online in the university library?
So this is not my thesis actually, but yeah, my thesis are published somewhere. Yeah.
So is it free for anybody? Is it free access?
I don't know. I think
sure.
You can check Tda server.
So, but we have we have an option in Canada in the Memorial University. Anyone can Google our thesis title, then they can get, have the access freely. So if it
I
is
think
possible,
we have the same thing. In
I can access to Osim's thesis, but I accessed from UT Dallas computer, so I don't know it's from our outside we can do it or not. I think you can do that. You can get access into his thesis.
So, or I would request Dr. Osim to send your thesis to Mamunur Rashid, because he is very much interested.
Yeah,
Okay.
sure.
Okay.
Okay.
Thank you.
Or we can put the link in the comment box if it's freely available. So thanks everyone for joining us tonight. We'll see you in the next session.
Thank you so much. Thank you.